In the today's lecture, I will discuss the limitations of valence bond theory and the molecular orbital theory. After studying this lecture, you shall be able to know about the postulates of the valence band theory, understand why valence band theory is failed, know about the postulates of the molecular orbital theory, and understand the molecular orbital diagram of homo and heterodiatomic molecules. Now, let us discuss the postulates of the valence bond theory. The valence band theory was given by the Hitler and London in 1927 to explain the formation of the covalent bond between the two atoms. The theory was extended further by Pauling and Slater in 1931. The main postulates of the theory are: a covalent bond is formed due to the overlapping of outermost half-filled orbitals of the combining atoms. The two half-filled orbitals involved in the bond formation should contain electrons with opposite spins. The completely filled orbitals do not contribute to the bond formation. Between the two orbitals of the same energy, the orbital which is non-spherical, for example, p or d orbitals, forms a stronger bond than that which is spherically symmetrical, that is s orbital. The strength of the bond depends upon the extent of overlapping. Thus, greater the overlap, stronger is the bond so formed. The atoms which unite to form a molecule completely retain their identities in the resulting molecule. And the valence of the element is equal to the number of half-filled electrons present in it. Now we discuss the limitations of the valence band theory. The valence band theory explains the bonding in a very simple way, but this theory has some serious limitations. Number one, the VBT has not been found useful in describing the magnetic properties of the compound, that is, paramagnetism exhibited by the certain ions and molecules is not explained. This theory failed to explain the formation of coordinate bond in the molecule, and this theory failed to explain the formation of odd electron molecules. Now, what is molecular orbital theory? The atomic orbitals combine together to form a molecular orbital in which the identity of both the atomic orbitals is lost. Characteristics of the molecular orbital theory. In molecules, electrons are present in the new orbitals called molecular orbitals. These orbitals are characterized by the set of quantum numbers like atomic orbitals. The number of molecular orbitals produced is equal to the number of atomic orbitals that are combined. During the formation of bond, the two half-filled orbitals with opposite spins combine to form two molecular orbitals, one of which is bonding and other is anti-bonding molecular orbitals. Molecular orbitals formed by the addition of the two atomic orbital wave function is known as bonding molecular orbitals. Molecular orbitals formed by the subtraction of the two atomic orbital wave functions is known as anti-bonding molecular orbitals. The molecular orbitals which do not take part in the bonding are known as non-bonding molecular orbitals. Electrons are filled in the molecular orbitals according to Pauli, Horn's and Aufbau rule. The stability of the bond is expressed in terms of bond order, which is defined as one half of the difference between the number of electrons in the bonding molecular orbital and anti-bonding molecular orbitals. So the bond order is half number of electrons in bonding minus number of electrons in anti-bonding, where Nb is the number of electrons in bonding molecular orbital and Na is the number of electrons in anti-bonding molecular orbital. Now, let us discuss the difference between bonding and anti-bonding molecular orbital. Bonding molecular orbital is formed by the addition of overlap of atomic orbitals, whereas anti-bonding molecular orbitals formed by the subtraction overlap of atomic orbitals. Bonding molecular orbitals may or may not have a node, whereas anti-bonding molecular orbital has a node in between the nuclei of bonded atoms. Bonding molecular orbitals, the electron density is more in between the nuclei, means electrons in this orbitals leads to attraction between them. Whereas in anti-bonding molecular orbitals, electron density is less in between the nuclei, means electrons in this orbital leads to repulsion between the atoms. In bonding molecular orbitals, the energy is lesser than the energy of atomic orbitals, whereas in anti-molecular orbitals, energy is more than the energy of atomic orbitals. Now, we discuss the properties of the covalent bond. In the properties of the covalent bond, we discuss about the energy level diagram of the molecular orbitals. There are two types of the energy level diagrams, type 1 and type 2. Type 1 corresponds to nitrogen type order, whereas type 2 corresponds to the oxygen type order. In nitrogen type order, for lighter elements, that is from lithium to nitrogen, the filling of the electrons occurred in the following order, that is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px equals to pi 2py, sigma 2pz, pi star 2px equals to pi star 2py, sigma star 2pz. In second type means oxygen type order, for heavier elements, that is from oxygen, fluorine, and the filling of the electrons occurs in the following order, that is 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, pi 2px equals to pi 2py, pi star 2px equals to pi star 2py, and sigma star 2pz. Now, let us discuss the molecular orbital diagram of type first and type second. Type first, in which lighter elements like lithium to nitrogen represented by this diagram, and type second, in which oxygen, fluorine, neon are the elements which is represented by this diagram. A very important point kept in our mind, the orientation of the p orbital are different in both type of the type first and type second molecular orbital diagram. Now, let us discuss the magnetic behavior of the molecular orbital diagrams. The magnetic behavior are of two types. One is paramagnetic and other is diamagnetic. If any electron in the molecular orbital is unpaired, which represents the paramagnetic behavior, whereas if all the electrons in the molecular orbitals are paired, that represents the diamagnetic behavior. Paramagnetic behavior attracts the magnetic field, which is represented by this diagram, and diamagnetic behavior opposes the magnetic field, which is clearly seen in this diagram. Now, let us discuss the molecular orbital diagram for homodiatomic molecules. Homodiatomic molecules are of two types. Type 1, which corresponds to lithium to nitrogen, and type 2, which corresponds to oxygen, fluorine, neon, etc. Let us discuss the hydrogen molecule, which is under the type 1st category. The electronic configuration of hydrogen is 1s2 and star 1s0. Now, let us see the molecular orbital diagram of hydrogen molecule. Hydrogen atom having one electron, that is 1s1. So both atomic orbitals combine to form two molecular orbitals, and all the electrons fill in the bonding molecular orbital. So the electronic configuration is sigma 1s2 sigma star 1s0. Then we calculate the bond order. Bond order equals to half Nb minus Na. Number of electrons in bonding molecular orbital is 2 and number of electrons in anti-bonding molecular is 0. So the bond order is 1. Now we calculate the magnetic behavior. This is diamagnetic because the last orbital is completely filled. Now we will discuss nitrogen molecule. The atomic number of nitrogen is 14. Let us see the molecular orbital diagram of nitrogen. Nitrogen atom consists of 7 electrons whose configuration is 1s2, 2s2 and 2p3. Means in 1s2 there is 2 electrons, in 2s2 there is also 2 electrons, and in 2p3 total 6 electrons in nitrogen molecule. Now we fill the electrons in this orbital from lower to higher energy state. Then we calculate the bond order. Half number of electrons in bonding, that is 10, minus number of electrons in anti-bonding, that is 4, which is equals to 3. So the electronic configuration of the nitrogen molecule is sigma 1s2 sigma star 1s2 sigma 2s2 sigma star 2s2. Pi 2px2 is equals to pi 2py2 sigma 2pz2. The magnetic behavior is diamagnetic in nature because all the electrons in molecular orbital are paired. Now we discuss the second type of molecular orbital diagram, that is oxygen molecule. The atomic number of oxygen is 16. Let us see the molecular orbital diagram of oxygen. Oxygen atoms contains 8 electrons whose configuration is 1s2, 2s2, 2p4. So in 1s2 orbital there is 2 electron, in 2s2 orbital there is 2 electrons, and in 2p4 orbitals there is 4 electrons. Now in oxygen molecule we fill the electrons from lower to higher. So we calculate the bond order. Half 10 minus 6 is equals to 2. The electronic configuration is sigma 1s2 sigma star 1s2 sigma 2s2 sigma star 2s2 sigma 2pz2 pi 2px2 is equals to pi 2pz2 pi star 2px2 is 1 is equals to pi star 2py1. The magnetic behavior is paramagnetic in nature because the presence of two unpaired electrons. Now we discuss heterodiatomic molecules. Let us see the example of NO. This is the molecular orbital diagram of NO. In one hand we take nitrogen atom and in another hand we take oxygen atom. Because nitrogen is less electronegative than oxygen, then we follow the second type of the molecular orbital diagram. The number of electrons is 7 plus 8 is equals to 15. Number of bonding electron is 10 and number of anti-bonding electrons in 5. Then we calculate the bond order, which is equals to 2.5. The magnetic behavior shows paramagnetic in nature because of the half-filled orbitals in the molecular orbital diagram. On the basis of our presentation, these are some practice questions, that is, explain the postulates of BBT, discuss the limitation of valence bond theory, what is MOT and discuss its postulate, explain the term paramagnetic and diamagnetic behavior, explain the difference between bonding and anti-bonding molecular orbitals, draw the molecular orbital diagram of oxygen, nitrogen and NO. These are some references which is used in our PPT. Thank you.